Hi, I'm Ben Chung, and today I'm going to give you a Bell Labs showcase tour. Now, Bell Labs, we do actually public showcase tours, and I'm one of the Bell Labs tour guides. So we see here, AT&T started in 1896. Western Electric buys this property on West Street, and that place, if you look on a map, is still called actually Murray Hill. And between 1925 and 34, it merges with AT&T Engineers. And by 1942, in World War II, there's 4,000 engineers and scientists, and they're really kind of piled on top of each other. And that's when they do a search for this new site in Murray Hill, and that's when Murray Hill was built. But in 1925 is when Bell Labs itself is incorporated, so we're about to come on the 100th year anniversary of Bell Labs. And they scouted a number of different locations in New Jersey, and today that's where we are in Murray Hill here. And so here's the showcase. Here's the Bell Labs showcase. This area is all about the communications. So Bell Labs in the 1920s does a lot of pioneering work to understand voice. They create the first touch-tone telephone. They lay down the first transatlantic cable, TAT-1, and eventually TAT-8 is optical. So there's yep, that's the first transatlantic cable. They also invent digital cellular, so they invent the concept of a cell phone. In 1946, actually, you could have only 3 subscribers in an entire city. So only just 3 people could make a call. But they develop the concept of a cellular system, and Bell Labs develops this 3-channel mobile system operating in St. Louis in 1946. So the city could only hold 3 calls, but they develop this concept of the cellular concept. And the cellular concept is like, it's like this. So basically, with the cellular concept, you can now have many hundreds of calls. So the idea is that frequencies used in these orange cells are exclusively used in those orange cells, and this is a geographical area, right? So, and cells can vary in size up to 20 miles in diameter, so you can have a very huge network, but they can also be much smaller, a mile. Now, today's cells in 5G are the FR2 gigahertz millimeter wave cells. They're only 100 meters or 490 feet. But the concept that was developed here in the cellular concept was developed by Bell Labs in 1971, and it's used commercially. It's developed in 1947 and goes commercial in 1971, which allows frequencies to be reused. So the frequencies used in this cell are reused here and here, so that users here won't affect a user over here, and that's how they at first with the time division multiple access and 2G, that they're able to increase a lot of capacity. So they also use radar to determine the altitude of an airplane. So that was one of the pioneering things they did. And this is a view of the undersea fiber optic cable, TAT-8, called the Transatlantic Cable 8, laid across the Atlantic in 1988, linking America and Europe. It's a 3,148-mile cable system, and it can handle 40,000 simultaneous telephone conversations, compared to only the 12 that was first laid in the 1956 system. Okay, so over here we have this is the first the first sound synchronized system. It's called the Vitaphone, and it has a 33.5 LP player here, and it's synchronized to sound. It's synchronized to sound with the film using a ratchet system, so it introduces in 1927 essentially the era of film with sound. So you see here, the first movie was the Jazz Singer. It features songs by Al Jolson, and it released at this theater here. You see at the Warner's Theater. And it was the first commercially successful system for producing sound motion pictures. So in the 20s and 30s, Bell Labs does a lot of research in understanding the voice, the human voice. They develop hearing aids. They develop a fax machine. They develop a synthetic speech systems. They really come to understand a lot about the human communications and voice, because that's near and dear to their heart. Here we have the first. This is the first fax machine that was ever sent. So they built the first successful system to offer continuous transmission of photographs. Yep. And this is the first television transmission. So we see here in 1927 from Washington, D.C., Herbert Hoover makes a transmission from Washington, D.C. to here in New York, and it's through Whippany in New Jersey. So this area is about communications and telephones and systems and movie systems that is pioneered by Bell Labs. This section here is about information technology. So Bell Labs does a tremendous amount of research in information technology. I'm going to point to this here. So this is the first, they have the first electrical digital computer. In 1937, George Stibitz uses a computer that has electromechanical relays, and it uses the components of a telephone switching system, and it's used to handle routine arithmetic problems, and it's seen as one of the first digital computers available in the age. So there's actually a plaque in the McNutt Hall in Dartmouth College that basically reads the first working electric digital computer was used here. Okay. So we'll come over here, Ken. This way. Okay, now one of the highlights of the showcase is actually the development of information theory by Claude Shannon in 1948. So in 1948, Shannon is a researcher at Bell Labs, and he actually during the war, it started before 1948, but in 1948 he publishes this seminal paper called A Mathematical Theory of Communication. But during World War II, he's actually doing some decryption. He has to find out how to create a code so that a message can be sent in a coded way that it couldn't be decoded. And he has this flash of insight that he determines that a message can be sent using this sort of like 20 questions system. So he says any message whatsoever can be sent through a series of sort of yes/no questions like you would in 20 questions. So if I'm thinking of, say, an animal, here, Liz, play with me, 20 questions. So I'm thinking of an animal, and just ask me sort of yes or no question.
Is it three-legged?
Is it three-legged, right? That would be a yes or no question. It's not three-legged, so no.
No. Is it bigger than a human?
Is it bigger than a human? No.
Is it a human?
It's not a human.
Does it live in the United States?
It lives, there are some of these in the United States.
So it's not four-legged, you said?
It's not four-legged.
Does it live in the ocean?
Yes, it lives in the ocean.
Okay. Is it saltwater?
Is it saltwater? Yeah, I'd say there's saltwater versions of these.
Okay. Is it on beaches?
It can be found on beaches. Yeah.
Is it, how many, does it have, you said it doesn't have four legs, does it have, I guess it does, but does it have more than 6 legs?
Yes.
Is it an octopus?
It's an octopus. Very good. Okay. So as you see, Liz basically, through a series of yes or no questions, we sent a simple thing on an octopus. But Claude Shannon has the insight that you can send any message whatsoever through a series of essentially 20 questions, yes or no questions. But let me see if I can illustrate. So play that same question again, but with a letter of the alphabet. Like, is it in the first half of the alphabet? Yes. Or is it in the second half of the alphabet? No. Is it in the, if it's in the first half of the alphabet, is it in the first quarter of the alphabet? Like A through M would be the first, maybe half of the alphabet, and maybe A through H is the first quarter of the alphabet. And through a series of yes or no, you can get to the letter B, let's say, right? Mm-hmm. So essentially, he has this insight that you can break down the communication letters just through a series of yes or no questions. Now today, we call that a bit and a byte, right? So I can represent, through a binary series of zeros and ones, I can represent any letter in the alphabet. Now today, that seems almost commonsensical to us. I mean, everybody's sort of a bit and byte. But he's really paving this wasn't so obvious. And as I talk about all these things, all these groundbreaking inventions and stuff, at the time, if you put your shoes in the time of the inventors, the time of the inventor, these questions aren't obvious, right? They're really key, insightful questions that a scientist asks, and from that they pursue and develop something really unique. So Claude Shannon really lays the foundation with his 1948 work, A Mathematical Theory of Communication. He lays the groundwork for today what is information theory, things that lots of coding methods follow from his work. He defines the concept of a sender and a receiver, a source, a transmitter and a receiver, and across a channel. So somebody's trying to send a message, they use some kind of system to send a message across the channel, and he mathematically describes the characteristics of the channel, and there's a mathematical limit to how much information you can transmit across a channel. And people develop coding methods in order to try to achieve higher and higher rates. Eventually now there's compression methods are also part of information theory, like zip files. You've probably heard of zip files. So Claude Shannon also has the insight that if there's a series of letters that are all the same, like some messages B B B B B, like I don't have to send 6 B's, I can just send a 6 and a B, right? Mm-hmm. So he has some insights already of how to compress information. So this is Claude Shannon is one of the seminal sort of highlights in the showcase here. And there's a few other things that are like that in the showcase, so we'll pause a little bit more on those. Okay, so come here. Now Bell Labs is doing a lot in information, just in information technology and information sciences. We're doing a lot in art and machine learning and artificial intelligence. And one of the first, if you look in here, one of the first, what's seen as a sort of pioneering thought in artificial intelligence is Shannon's mechanical mouse. He calls Theseus, and is able to actually he's actually able to run a maze, right? So it's seen as one of the first artificial intelligence in 1950. He creates this mechanical mouse capable of running a simple maze. And this is a view of his seminal work. a mathematical theory of computation in 1948, a really seminal paper in information theory. Okay, now in this table here is a lot about pure science. Bell Labs pioneers radio astronomy. So here we see a model of the first approximately 100 feet long and 20 feet tall. This is Jansky's radio telescope that rotated on tires, and it could pinpoint an astronomical radio source. So while looking for sources of static and radio transmissions, Karl Jansky was the first person to detect radio waves coming from outer space. And the source of these signals, radio noise at a wavelength of 14.6 meters, is at the center of our Milky Way galaxy. And this discovery in 1933 marked the beginning of the science of radio astronomy. So over here we see basically one of the two people that won the Nobel Prize in 1978, Arno Penzias and Robert Wilson, are awarded the Nobel Prize for their discovery to they isolate the cosmic wave radio background radiation. Basically, there's energy that's coming. They detect from their system here. Energy that's coming from all over the everywhere, right? Basically, so they detect. So we see here basically their research is gives credence to the Big Bang theory. They observed basically the first formation of light from 380,000 years after the Big Bang. The very first light is sent, and so when they discover this cosmic wave background radiation, it's essentially energy that's coming from everywhere, all around them. And what could they ask? What could be causing that energy? They try to remove all possible sources. Maybe it's their detector, and after they try and clean their detector and everything, they realize this energy is really coming from everywhere. And what could be causing that? And they basically what they find is that they're essentially detecting the very oldest photons in the universe, right? So from just 380,000 years after the Big Bang, which is one of the reasons why I think they're given the awarded the Nobel Prize in 1978. So essentially, what they're listening to, what they detect, is basically the oldest photons in the universe, and we're still there's now. NASA has launched satellites and things to detect and map out this cosmic wave background radiation. Another Nobel Prize was the optical tweezers. Arthur Ashkin invents these optical tweezers to grab particles, atoms, and viruses with like laser beams. And lasers were also invented at Bell Labs. And this breakthrough is the byproduct of research of fundamental communications. So next we have something called the fractional quantum Hall effect. Now, this is something that's really, really very interesting, and it's one of the more interesting phenomena, I think, in physics. So if you have a metal and you apply a magnetic field, normally electrons will kind of flow kind of like a river. But if you have a very thin semiconductor and you apply a magnetic field, there are these little sort of eddies that are formed. And these little eddies are called Landau levels. And so the electrons don't kind of just randomly flow, but rather they kind of flow in these little sort of eddies. And what the result of that is that the resistance of a normal metal when you apply a magnetic field is it's a very linear sort of thing. But with the quantum Hall effect, the resistance is stepped. So there's fixed levels of resistance, and that's due to these little sort of eddies that occur. So essentially, what you observe is you're observing a quantum level effect at a macro level. And that's a very unusual thing to detect. It's not a normal sort of thing, because the quantum world is a very weird weird effects can happen, and these quantized levels of resistance are very unusual and very interesting to observe. And he won in 1982 he wins the Nobel Prize for that. So there's a lot of pure research and science that's done by Bell Labs. Again, they invent radio astronomy. They're super famous for detecting the cosmic wave background radiation to give foundations to the Big Bang Theory. Okay, so here, of course, one of the most famous things that Bell Labs does is they invent the transistor. So the transistor is one of the most significant advances ever made at Bell Labs. It's invented by William Shockley, Walter Brattain, and John Bardeen in December of 1947. And the development of the transistor, the first solid-state amplifier, replaces the vacuum tube and lays the foundation for the solid-state microelectronics revolution that continues today. So if you go here, this is the actual world's first transistor. So we see here, this is the actual first transistor ever made. So you can see here in that little tiny thing there, about 1 centimeter in size. It's a germanium point contact transistor. So you know, that is the basis of that was a revolution. And entire industries were made, you know, from because of that. So let me try to explain a little bit what's happening here. So the let's go to where there's more light, I guess. So we here see basically the transistor has a gate. It has a body, it has a source, and it has a drain. And it can do one of two things. Basically, it acts as a switch, or it can amplify a signal. So, because it's a solid-state device, there's no moving parts, and it doesn't break down like vacuum tubes. And the fact that it's a super tiny switch is why we have all the amazing electronics that we do today. Now, why does this work? Well, basically, silicon. If you look at the properties of the atomic orbitals of silicon, it's got 14 protons and neutrons, and this is the s orbital. So the first shell has 2 electrons, and then this outer shell has 8 electrons, and in the outermost shell has 4 electrons, and that outermost shell is called the valence shell, and so it has 4 electrons that can essentially pair with something else. That's why we see when silicon forms a lattice, like a structure, like it makes a rock or pebble or sand. It's basically a silicon lattice there are 4 partner silicon atoms around it, because these electrons, these outermost electrons, are basically bonding with another electron from another adjacent silicon atom. And now, if it were just that, that wouldn't be so special. So what's interesting about silicon is that it's not a conductor per se. It's not great at being a conductor. It's not great at being an insulator. It's what's called a semiconductor. So it has by itself, it's nothing special, but when you dope it with what's called doping, you add a phosphorus atom that has also it has 5 electrons in its valence orbital, so it can fit in the lattice and it has an extra electron. You dope another part of it with boron that's missing one. It only has 3. It has 3. It has 3 electrons in the outer orbitals, and so when you have these together, this N-type and P-type electrons, these electrons can travel from one place to another, and that's how it can act as a switch, essentially. So that's the basis of how a transistor works, and it really revolutionizes an industry. Now, the first transistor they have is a point contact transistor. By 1971, there's 20,000 transistors in the same 1 centimeter square, and today there's billions that fit in that same space. So, okay. Yeah. Okay, so we just finished talking about the transistor. It revolutionizes the electronics, and it creates an industry, and a lot of some of the key Bell Labs inventions have created entire industries. The movie industry with the Vitaphone, radio astronomy, and the transistor, of course, is in all of the basis of all of our modern electronics. So here we have advances in what's called sustainability, and here is another a Nobel Prize winning device. It's called the charge couple device. It was invented by George E. Smith and Willard Boyle at Bell Labs in 1969, and originally conceived as an information storage device. But it soon becomes obvious that this two-dimensional array of CCDs is a superb imaging device. So we see in here is the linear shift register developed by Boyle and Smith in 1970 to demonstrate the charge-coupled transfer principle, which is the basis of CCD operation. And below that, you can see a two-dimensional CCD image chip from 1971, and it's one of the first CCD image devices ever made. Now, Boyle and Smith, they're looking at magnetic bubble memory, and I'll explain briefly how, because this is such an important thing. I'll explain briefly kind of how this works. So basically, when light hits the surface, when a photon comes in, it excites this semiconductor, the silicon layer, and it charges a capacitor. A capacitor is able to store an electric charge. And what's going on is that when this array is charged, it's like a bucket brigade. What happens is these charges are shifted down in this case. So the one that was here goes here, the one that was here goes here, the one that was here goes here, and the one that falls off is red. So they convert this this output charge into a signal. And what happens is basically you can read this signal, you can read that signal, then you push that one off, you read that signal, you push the next one off, and you read that signal. So the amount of electric charge is proportional to the amount of energy, the amount of light that's hitting this cell. And this is now, we call this a pixel. Okay, so this is a 4x4 or 4x5 20 pixel system, basically I'm showing you. And essentially what's happening is the amount of charge here is, and you got to think their first ones are black and white. Okay, color comes much later. So their first charges are basically black and white, and this is and it's just one-dimensional actually. So you can imagine what's happening is the very first CCD is just a simple row. Okay, it's not two-dimensional, and this concept of this bucket brigade, it's actually based on what's called a bucket brigade device in 1971. And that concept used in two-dimensional is the basis of modern imaging systems and cameras, and the CCD, charge coupled device concept, wins them the Nobel Prize. And eventually, engineers in Kodak figure out how to do a colored device. What they do is they have a filter. So they have, instead of a single thing, they have a 2x2 thing that's used to represent 1 pixel, and it's 1 is red, 2 is green, and 1 is blue. So it's a RGGB system that detects the amount of. It's the similar sort of concept as this, except the one that's filtered for blue is responsive to blue light, and so its charge is based on the amount of blue light that hits it. There's 2 green cells, so the amount of charge for the green cell is how much green light hits that, and then the one for red, green, and blue, the one that is for red and green and blue, the one that blue light hits it. So for that one cell, it uses multiple, basically 4 cells to represent. 4 cells are used to represent R, G, and B, red, green, and blue. And because your eyes are actually more sensitive to green, there's 2 green cells. And that's how a color CCD works. So that forms the basis of digital cameras and imaging. There's a number of other sustainability devices. We developed the CAT algorithm, which uses which is the basis for computed axial tomography. It uses what's called a radon transform and backpropagation, and as an X-ray passes through a target, a body, it's attenuated, and it can be mathematically backpropagated to figure out how much attenuation it was, and as you rotate it, that's how you get a medical image. We developed in the early 20th century. Western Electric Bell Labs makes a contributions in the development of a modern hearing aid. And in 1990, Bell Labs biophysicist Seiji Ogawa develops this functional MRI, functional magnetic resonance imaging. And over here we have, in the early 1950s, Bell Labs actually pioneers the development of solar cells. So we're able to actually develop the first solar cell. And early on in 1929, we developed an artificial larynx too. So you see here, in 1929, Bell Labs develops the first artificial larynx. Okay, so we'll move here, and so in 1957, the space race is on. The Russians launched Sputnik. It's the world's first satellite, and basically it's just a little ball, like maybe yay big, and all it does is it beep beep beep. It sends a steady beep from space, and it's orbiting space, and that causes America to start the space race. John F. Kennedy at Rice University says before 1970, before the decade's out, we want to launch a man on the moon. Even though at that time he made the speech like we're infants in space rocketry. But even at that time, Bell Labs has the idea of using space for communication. Now, at that time, we already have microwave towers for television across America. We're able to use microwave towers for communications. But we have Bell Labs has this vision to have a microwave-based communication to send television signals across the Atlantic from the U.S. to Europe. But in order to do that, you'd have to have an impossibly tall tower, microwave transmission tower, to make that happen. But they asked themselves, well, what if we could send that from space? I mean, that's essentially a transmission that would be tall enough to make that happen. So in 1962, if you look above, this is the Telstar 1 satellite. So this is the satellite which hosts the first transatlantic television transmission. It's launched in 1962. It has 3,600 solar panels around it to power it. Along its equator, along its belt, it can take in at 8 gigahertz, it takes in a transmission and beams it back down to Earth at 4 gigahertz. So the towers that receive it are 90 feet tall. And it hosts, in 1962, it hosts the very first television transmission. John F. Kennedy makes his address through it, and the first transatlantic telephone call is made between the vice president and the president of AT&T. The first images are sent through Telstar 1. It's an image of the Statue of Liberty. And it's really, it pioneers basically transatlantic communications. And Telstar 1 and 2, our Bell Labs are involved in that. But now today, the Telstar name continues to be used, but really just it was Telstar 1 and 2 that Bell Labs pioneered. So, and today, of course, there's a lot of things that are done by Bell Labs today for in the 20th century. We're pioneering a lot of things in artificial intelligence and machine learning and robotics. We're engaged in 5G, what's called 5G Advanced, and now 6G. And there's a lot of work we'll deploy the first lunar network. We're pioneering a lot of things and innovations in a lot of communication technologies and what's called massive MIMO, multiple input, multiple output. So we see here there's an example of basically, this is an example of a radio transmission that's kind of all over the place. But with MIMO, you can actually steer that. That's based, the original idea was based on phased array radar, but that allows the RF energy from an antenna to be steered and to greatly increase the efficiency of radio transmissions. So, okay, so that's it. I hope you enjoyed the Bell Labs tour, and be sure to check out some of my other videos. Thanks.